Thank you very much for coming along tonight. I'm really impressed by the great turnout, and it's a lovely venue as well. Predictably, we're beginning to get some rain outside. It's dry right now, isn't it? But certainly in Sheffield earlier today, it was beginning to rain again after what's been a fairly dry month, and actually following a record wet June in the country last year. June's actually been quite dry so far, hasn't it? But perhaps the weather's becoming a little bit more unsettled now. But it does demonstrate the great variability, doesn't it, in our weather conditions that we get from year to year, from season to season. I should say that there's a lot of international work going on this, and although it's just my name on this slide, I'm working with a lot of other people around the, both nationally and in other countries on this. I will acknowledge some of them as I go through the talk. There's a lot of people involved in this research. So what you've got there is that red ribbon or yellow ribbon is showing the what we call the polar jet stream as it's widening its way across North America. It's going up over the Rocky Mountains, back down the other side, down the east of North America there, and then out over the North Atlantic towards the UK and Iceland, actually. UK is just off the top right of that slide. Next slide, please. So what I'm going to talk about, I'm going to give a brief overview of global warming and extreme weather conditions and the relations between the two. So the relation between the climate change, which is perhaps traditionally thought of as been a much slower underlying process, although it seems to have sped up in the last few years and decades, and the kind of extreme weather conditions that we tend to experience perhaps on a shorter time scale. Such as the extreme rains that we had last summer, for example. I'm going to mainly talk about summer, as been suggested, because there's not time to cover everything, but we're in summer, so it's very topical to talk about summer conditions. A lot of my own research has been in the summer as well, but if you've got questions about other seasons, I'm happy to try and address them at the end, perhaps might be the best place for doing that. I'm going to talk about jet stream and a pattern of winds across the North Atlantic that we call the North Atlantic Oscillation. It's like a kind of cycling of the wind variation, wind strength and position across the North Atlantic. It's got this technical term, it's called the North Atlantic Oscillation, and it's related to the jet stream variations. It's actually the main way that climate scientists have actually used to define the variation in winds across the North Atlantic that affect the weather conditions in the UK is using this pattern of winds across the North Atlantic. So I'll explain that in a bit. So after defining the jet stream, I'll go on to talk about recent jet stream changes and their effects on the summer climate in England, the UK, but also in Greenland, because a lot of my work has actually been looking at the climate and climate change in Greenland, as well as in the changes in the mass of the ice sheet in Greenland. And that's how I became more involved in this jet stream research or the changes in extreme weather in the UK. It was actually because I noticed some strange weather patterns going on over Greenland that are actually almost certainly connected with some of the strange weather patterns that we've been noticing in the UK in the last 6 summers. So I will try and make some links there because I think this is all interlinked. And that's the direction that I've been coming from because a lot of my work's actually been concerned with changes in climate in Greenland. Next slide, please. What I thought I'd show you is actually, this is, I believe, the longest running official weather station in the Yorkshire region is one which is just a few hundred metres from where I work in the university at Sheffield. It's got a picture of the thermometer screen, which looks a bit like a beehive in the top left there. And that's run by the Museum of Sheffield in Sheffield Weston Park, fairly near the centre of Sheffield. Probably many of you have already seen this on visits to Sheffield. How many of you have been past this or seen this or know about this? Probably some of you, a few of you, yes. Yeah. So next time you're in Sheffield, this is right by the museum. But this is a Met Office station. So it's the official station in Sheffield. As I say, it's got the longest running official weather station records from the Yorkshire region. It goes back to 1882. It's an almost unbroken record. And using that record, we're able to build up a fairly comprehensive overview or picture of how the climate has been changing locally in Yorkshire, or at least in Sheffield, since the late 19th century. So what the top graph is showing, you can really ignore the bottom graph for the moment. The top graph is, the red line is showing the temperature variations in Sheffield since 1882. So the left hand, this is 1882 on the left hand side of the graph, and then this is going all the way throughout the Sheffield record to the 2000s, which is the last decade on the right hand side of that graph. You can see that these are not actually temperature values, these are changes in temperature, or what are called temperature anomalies. It's showing when there have been cold periods or warm periods relatively in the record. You can see that the red line on average has been going up. There are a lot of short-term blips in that red line, but you can see there is a strong warming trend over the last 130 years or so. But what's interesting on this graph is that the green line, you can see that there's a green line as well as the red line. The red line is the temperature record, the air temperature record from Sheffield Western Park. The green line is showing the global temperature variations or the average northern hemisphere temperature variations for the same time period over the last 130 years. And you can see that although clearly there's some differences in the short-term fluctuations between the red and the green lines, in terms of the overall trend in temperature and the sort of longer-term variations, they are quite similar. So in other words, this is very good observational evidence that global warming, it's just over a 1 degree Celsius warming there, something like 1.2 degrees Celsius in Sheffield, warming over the last 130 years or so. It's very good evidence from this Western Park weather station in Sheffield that's run by the Met Office of global warming happening on our doorstep, so to speak, or at least 40 miles down the road in Sheffield. You'll get a very similar signal in Leeds with weather stations here, except that I think the Sheffield one is slightly longer running. As I say, it's the longest running in Yorkshire, which is one of the reasons why I show it here. Also because I work in the university and it's one that's right by me, so it's excellent to show the students and people in Sheffield this is evidence of global warming going on right on our doorstep. And in fact, the lower graph, this is actually showing, actually this is now the last 1,000 years of global temperature estimates, and the orange, this is actually what's blown out to the top graph, is this small orange segment on the right hand side of the bottom graph is showing the 20th century, and the global temperature, you can see a sharp increase over the last 100 years compared with the previous 900 or so years, according to our best estimates from various reconstructions, from thermometers, but also from tree rings and ocean sediment cores, and various estimates of the global temperature variation going back some hundreds of years into the past. Next slide, please. So, really, that was just an introduction. Global warming is really happening, and you can observe it on our doorstep in Sheffield. But global warming is not uniform, it's not the same everywhere. If you look at a map of how the temperature has varied across the world, which is what this map is showing, this map is actually showing the temperature differences for the last decade, or for a period, yes, it's 2002 to 2011, it's more or less the last decade. It's how much warmer it was over that last decade compared with the 1951 to 1980 period. So these the yellows and oranges and reds on the map there. It's a global map, and the UK is somewhere top centre of the map. Antarctica's down at the bottom. It's covering the whole world. Is basically where you have the oranges and reds. You have a greater temperature difference for the last decade compared with the previous 30-year period, 1951 to 1980. Whereas where you've got the whites and lighter yellows, there are a few areas actually that are cooler in the last decade than the earlier 30-year period, but the last decade in general is warmer nearly everywhere. But you can see that the areas that have the greatest warming in the last decade compared with that previous 30-year period are the sort of the high latitude areas in the northern hemisphere. So in other words, the Arctic and Greenland and parts of northern Canada, Alaska, parts of northern Siberia have all warmed very dramatically indeed over the last 10 or 20 years actually, compared with the previous few decades. So that the temperatures on average in the Arctic are somewhere around 2 degrees Celsius warmer for the last decade than they were during the mid to late 20th century. Now, in other words, the rate of global warming in the Arctic has been at least about double that elsewhere in the world at lower and middle latitudes. And there are reasons for that we'll have a look at a bit later during the talk. But basically, global warming is not uniform. There are regions of the world which have warmed more strongly than others, and this is linked in with changes in perhaps changes in ice cover which are enhancing the warming in the Arctic compared with areas further south. And we'll look at that in more detail a bit later. Next slide, please. Now, actually, of course, it's only, well, I'm sure we all remember good summers and poor summers in this country, in England and in the UK, in the British Isles. We all remember good summers and poor summers. But actually, we haven't had a really good summer for a few years now, have we? In fact, I was giving another talk to some colleagues in Sheffield. We have a field station out in the Peak District, and there's some overlap in the slides. But I remember saying to them that 2006, I think, was the last reasonable summer we had in over large parts of England. And to have a really good summer, you have to go back to 2003. I don't know how many of you remember that. 10 years ago, we had a really hot summer. It was actually more pronounced in the southeast England, but I think even in the north it was quite a good summer. And in fact, this map here, this is actually showing the temperature anomalies, or how much warmer or colder than a normal summer it is for 2003. So again, you've got oranges and reds on this map of Europe, which is actually showing the temperature anomalies for summer 2003. It's reds over Central Europe in particular, but also over the UK. But this summer was really very unusually warm indeed in the Swiss Alps and in Austria and in France. And in Paris it was over 100 degrees Fahrenheit for some days on end. There were many thousands of extra fatalities due to heat-related deaths in Central Europe because of the intense summer heat that went on for several weeks on end, particularly in June and August in 2003. And actually, there have been some scientific studies that have been carried out into that summer. It was a very unusual summer in the context of the previous 100 years. Perhaps the probability of getting those summer conditions was something like 1 in 10,000, or certainly less than 1 in 1,000. It's a very unusually hot summer. And the suggestion was that according to the computer model simulations of future climate change, that we might expect an increased frequency of these summers as we go ahead in the current century. So as we go ahead, say, in the next 50 to 100 years, or even sooner, you might expect this kind of summer to become less rare than was the case according to the previous climate conditions. Because as you increase the average temperatures, you can get a disproportionate increase in the extreme events or conditions. So the idea was that perhaps by 2050, this summer might be one every 4 years, or 1 every 6 years, or certainly a lot more frequent than it would have been before. It was an exceptional event. There was a lot of extra melting of ice and snow, and the glaciers in the Alps lost something like 1% of their mass in that summer. It was an extraordinary event in terms of an extreme climate event. Now, you can't use any single extreme event to say that climate is definitely changing, but what you can do is to look at how these events statistically change over time, whether there's clusters of such events, how they change in their frequency and intensity, to say something about climate change on a longer timescale. But this was an extraordinary rare event, and the suggestion was that we perhaps might expect more of these as we go ahead into the next, say, 50 years or so. Next slide, please. But the weather being as it is, it's always very complicated, isn't it? So actually, what we saw in, well, I'm actually jumping ahead to last summer first of all, but in 2012, last summer, this is looking for June, July, August, you can see that large parts of England and Northern Ireland, and Wales as well, and South East Scotland are covered with blue. And of course, this is actually a map of the showing the amount of rain basically across the country. It was record levels in England last summer. In fact, last year, England had its wettest year since records began. National rainfall records began in 1910, so that's for over 100 years of national rainfall records. And not so much in northwest Scotland, which is interesting because the jet stream was further south than average, so actually northwest Scotland had quite a dry year last year. But large parts of the UK or the British Isles were very wet last year, and also last summer, not just last year. So this map is actually for last summer, for June, July, August, and it's showing that large parts of the country had nearly double their normal rainfall that you'd expect in a normal summer. So, in other words, we've had events that perhaps we weren't expecting, or, well, there's always variability in weather conditions anyway, but, you know, as well as having a record warm year, and a new national highest temperature being recorded of somewhere near 40 degrees, 38.5 degrees Celsius, wasn't it? A new UK national temperature record in 2003, and that summer heat wave that I've mentioned in the previous slide. We've also had since then a couple of unusually wet summers that have broken national records. So it wasn't just this summer, which is last year. It was unusually wet last summer, wasn't it? And particularly June was very, very wet. June was a record wet month in the national June rainfall records last summer. But if you go to the next slide, we also had a few years ago, June 2007, I'm sure you all remember this, but where I'm based in Sheffield, we had some devastating floods also in Hull as well, but also elsewhere in the country, in Gloucestershire, and many places around the country, in central England actually as well. But Yorkshire and Humberside and Hull area were particularly badly hit, weren't they? So this was in 2007. So in other words, last summer doesn't just seem to have been an isolated event, but we seem to have had a run of unusually cool wet summer weather, of which these 2 years, 2007 and 2012, are the most extreme examples. But if you look at the other summers in between, they haven't been anything to write home about, have they, in terms of having hot, dry, sunny summer weather. On the whole, the conditions have been rather cool and rather wet for the last 6 summers in the UK, at least in England. Not so much in North West Scotland, which is interesting, and we'll sort of touch on why a bit later. But you can see this deep blue area here. This is showing in 2007. This is a map for June 2007, showing how much more rain there was in that year in June compared with the normal June. And in fact, in the Yorkshire area, we had 4 times the normal June rainfall in June 2007. We had these tremendous surface floods in Sheffield, and a couple of people were killed, unfortunately, but we had major rescue events to airlift people from roofs of office blocks and cars floating down the main streets in the city centre of Sheffield. So it was quite, there was chaos and havoc for a while actually. And Sheffield was the top news story internationally for a few hours, in fact, because of this event. And Hull had very bad flooding as well. Anyway, next slide please. So of course, what we've all been noticing is these sort of changes in summer weather conditions over the last 6 years, becoming perhaps cooler and wetter than we've been used to experiencing over the last few decades prior to 2007. And we have to ask ourselves what may have triggered these changes in summer weather conditions. Well, it's largely down to, you've probably heard increasingly in the news recently, there have been these changes in the what we call the jet stream, which is basically a band of high altitude winds in the atmosphere where a lot of storm systems develop that bring strong winds and rainfall to the surface of the Earth in places that are more or less underneath where the jet stream track is winding its way, higher up in the atmosphere. So this map is really showing, well, we've got a couple of charts here. The map on the top right is showing basically this is an attempt by the Earth to redistribute the heat from the equator where it's too hot, there's too much heat energy coming in from the sun at the equator, to the poles where it's too cold. So the red arrows are basically showing they're going outwards in either way, from the equator, which is in the middle of that blue square at the top there, and towards the poles where it's cooler. This is a sort of a transfer of energy, and this is done partly through the jet streams. They're these sort of air currents that transport heat and energy from regions further south to regions further north in both hemispheres to try and sort of redistribute this sort of heat to balance out the sort of energy budget in the atmosphere. Also, there's currents in the ocean that do a similar thing. I won't so much be talking about those ocean currents this evening. But the map on the bottom left, this is really showing the strong band of winds in the atmosphere, showing where you've got the reds, oranges and yellows here. And the sort of white lines are showing where you get surface cyclones or storm systems that are developing at the surface, because basically it's linked in with a lot of eddies and storm systems forming at the surface. The air masses, you've got cold polar air to the north, which is shown in blue, and warm tropical air to the south, which is shown in red. They don't very readily mix, and there's a lot of stirring up of these air masses, and cyclones, low pressure systems forming as a result. You get the air masses being lifted up, higher up into the atmosphere, which causes them to become more unstable. And like a sponge being squeezed, you get more, you get a lot of rainfall, precipitation being formed from these storm systems. And because of the turbulence of these air masses that are mating, you get strong winds which are produced at the surface as well as the rain. So if you're under particular branches of the jet stream, or the main axis of the jet stream, then you can expect a lot of these low pressure systems, storm systems, strong winds and cyclones, low pressure systems coming across your part of the world. But if you're somewhere else, then you might expect perhaps no rain and drought-like conditions. So it all depends what weather conditions you experience and where you are on the Earth's surface in relation to the jet stream. Next slide, please. Now there's this thing that I mentioned earlier, which is basically, it's a measure of the strength of the winds across the North Atlantic Ocean going from south to north, and it's called the North Atlantic Oscillation. Probably some of you have heard of it, but basically it's measuring a gradient in the air pressure between further south in the North Atlantic, so around the Azores Islands in the centre of the North Atlantic, minus the air pressure in the region of the North Atlantic around Iceland, much further north in the North Atlantic. And basically, the winds in Earth's atmosphere follow the air pressure gradients. So there's high and low pressure systems in Earth's atmosphere. The winds revolve around those. And so the winds that form, that bring us our weather, depend on the positions and strengths of all these sort of high and low pressure systems in the Earth's atmosphere, which in turn, the high and low pressure systems, well, particularly the low pressure systems and cyclones, I've just mentioned that those fall along the route or axis of the jet stream. So basically, if the jet stream changes position, it can affect it will affect the strength and position of the surface winds over the North Atlantic, which influence, to a large extent, the weather conditions over the UK, because we're a very maritime climate, so quite often we get these westerly winds, which are coming in from the North Atlantic, which bring us sort of cloud and rain-bearing weather systems from the North Atlantic. But if the North Atlantic oscillation is stronger, that means you've got stronger westerly winds. If you've got a more positive North Atlantic oscillation, that means you've got a greater pressure difference between the south minus the North Atlantic, which means you've got stronger westerly winds, which are affecting the British Isles, which tends to give us cloudier, wetter weather normally, particularly in winter. Whereas if the North Atlantic oscillation is weaker than normal, then that pressure gradient across the ocean weakens, and then the westerly winds weaken, and we tend to get in winter drier, colder weather, and sometimes easterly winds bring us in severe cold winter spells from Siberia, as the high pressure can extend across the UK from an easterly point of view. So basically, sorry, next slide please. Basically, these changes in the North Atlantic oscillation, this is actually shown for winter, this slide, although much the same concept applies to summer. Basically, if you've got a more positive NAO conditions, North Atlantic oscillation is NAO, then you've got strong high pressure further south, strong low pressure further north. You've got this blue track of the jet stream, which just point to it with my pointer. This is, you can see you've got this very strong jet stream in a sort of linear fashion. It's coming across the UK, where the UK and England, this is to the right of the slide. On the other hand, the jet stream, sometimes it's weaker and meandering, and you can actually have this, what we call a negative NAO, where the pressure gradient is much weaker going south-north across the North Atlantic. So you've got weaker higher pressure in the Azores, weaker lower pressure over Iceland, and the westerly winds have weakened quite a lot. Sometimes you actually get a reversal of the winds, so you get easterly winds over England and the UK, and you can get actually a much weaker jet stream that can actually track, say, further south or sometimes further north of the UK than normal. So essentially, changes in the jet stream are strongly related to changes in the weather systems and winds that we experience in this country. So, in other words, any change in that blue line on these graphs is going to fundamentally affect the weather and climate conditions that we experience in this country on a seasonal basis, even on a daily basis, in fact, ultimately. Next slide, please. And in fact, this is actually showing the North Atlantic oscillation over the last century or so. Just look at the red line. In fact, if you jump to the next slide, this shows the same graph. Next slide, please. This is the same graph, but with a clearer lines, because I've done some averaging of the year-to-year fluctuations to smooth out some of the high-frequency variations in the data. So just look at the red line here. It's around about the zero line for much of the graph, but can you see in the last 10 years, since about the year 2000, the red line goes down on the graph. Can you all see that? And that's suggesting, well, that's showing that the North Atlantic oscillation has gone more negative in summer over the last decade. which means that we've had a weakening of the jet stream, a weakening of these westerly winds compared with normal conditions. But actually, it's, what's actually happened is the jet stream in summer is north of the UK anyway, so if it weakens, it comes further south and affects the UK more. So ironically, even though the jet stream has weakened in summer, it's actually giving us more rain because of the position has changed. It's come further south over the UK than normal. So actually, we're having more of these low pressure systems that are affecting us in summer if the North Atlantic oscillation goes more negative. It's an opposite effect to the winter. In winter, a more negative North Atlantic oscillation will actually give you drier, colder conditions on average. But because we're looking at summer, this is why I really just wanted to focus on summer. Because of the different jet stream position, what happens is that this trend in the last 10 years in the pressure gradients across the North Atlantic is indicating a jet stream that's come further south across the UK and has actually brought us more rain-bearing weather systems in the last, well, particularly 6 summers compared with in the 30 or 40 years previous to 2007. Next slide, please. So what caused this jet stream to vary? What factors can be influential? I'm only going to really focus on 2 for the purpose of this talk, although just be aware that there's a whole variety of factors. This is not an exhaustive list and there's still ongoing research. But I'm going to look at variations in Arctic sea ice cover and changes in snow, so reduced amounts of ice and snow in the Arctic. There's a theory or hypothesis that changes in the Arctic, in the snow and ice in the Arctic, may have influenced the jet stream position in the summer, which in turn has affected the summer climate in the UK. But there are other factors which cause the jet stream to change. So, for example, temperatures, sea temperatures across the North Atlantic Ocean, because this is indicating the amount of energy, in part, that can be available for driving the jet stream. Comes from the exchange of energy between the ocean and the atmosphere. So by measuring sea temperatures, we've done this through satellites, for example, and they do vary quite a lot from year to year. So this is another favoured theory for what can also cause the jet stream to vary. So there's other factors as well that your chairman mentioned solar variability at the beginning of the talk, which is changes in the amount of energy that's coming from the sun. Nothing to do with human effects on climate, but again, it's been suggested that this can affect the jet stream position and strength, probably more likely in winter, so I'm not likely to talk about solar variability here, even though it's something I'm very interested in, because that applies more to the changes in the winter jet stream rather than the summer jet stream. There's other things as well. There's air-sea interaction in the Pacific Ocean. It's called El Niño Southern Oscillation, which is basically changes in wind conditions and in sea temperatures in the Pacific Ocean can have knock-on effects on jet stream positions in the Atlantic and Indian Ocean. This has been shown to definitely have some influence, but again, it's possibly a smaller effect on the North Atlantic jet stream, and I'm not going to really talk about it anymore here because that could be a separate talk in its own right. But you need to be aware that there are these other factors that are all acting together in effect. So I'm just going to concentrate on particular ones that I've been focusing on with some colleagues in research that we've been doing, which are the top 2 factors on this slide. Next slide, please. So you're probably all aware that there's been a huge reduction over the last 10 to 20 years in the amount of frozen ocean in the Arctic, particularly in the summer. And this is shown by the white region here. This is actually showing the Arctic sea ice in September, on September the 16th, 2012. And this is at the time, the Arctic sea ice, it waxes and wanes seasonally, doesn't it, in response to the seasonal temperature cycle. And September is the time each year when the sea ice reaches its minimum area of coverage in the Arctic. But just look at this yellow line. The white is showing where the sea ice actually was last September, but where it should have been according to the last 30 years or so is shown by the yellow line. It should have actually extended out to cover this blue area here between the white area and the yellow line. So this is actually showing you how much lower than average the sea ice was last September compared with the average September for the last 30 years, because satellite records go back just over 30 years to the late 1970s. So actually last September was a record minimum in the Arctic sea ice cover, and we're talking about huge losses in the cover, something like 30–40% reduction over the last 30 years. 40% reduction in the cover. It's not just shrunk, it's also got a lot thinner as well. So the actual volume of the ice has gone down by something like 60%. More than half the amount of ice, sea ice in the Arctic in late summer has been lost over the last 30 years. Next slide, please. And, sorry, go back one, this graph, please. Yes, this is actually showing, just look at the red line on this slide, this is showing the amount of sea ice in the Arctic, or the percent changes in sea ice in September in the Arctic for the whole satellite record. And last September was here. It's a record low year, but this is showing percent changes or percent difference. You know, you've lost almost half the sea ice cover in September, for the month of September in the Arctic. Next slide, please. Now, what does that do? What effect does it have, losing all this extra sea ice in the Arctic? Well, what it does is it opens up a large area of ocean, so we're able to sail ships across areas of the Arctic that were formerly frozen. And of course, you've got a lot of political arguments about opening up the Arctic, and you know, energy companies and not oil companies wanting to exploit and you know, try and tap into new reserves given our dwindling energy resources, and you know, implications for tourism as well. But what it does in climatic terms is the big red arrow on this slide is showing that when you open up all that extra area of the Arctic Ocean by melting more sea ice cover, and the sea ice cover is melted because of global warming basically, or a large driver for the sea ice loss is global warming, almost certainly through greenhouse gas activities, through human activities. So there's some natural variation as well, but probably the main signal is the greenhouse gas warming through human activities of that Arctic sea ice loss. What you actually do is it actually amplifies the warming in the Arctic. Do you remember that a few slides ago I showed you that the region of the world where it had been warming most strongly is the Arctic, the high latitude northern hemisphere. And one very good reason for this is this red arrow here. So as you're melting more sea ice, removing more sea ice cover, then you're actually increasing the heat flux from the ocean. In the autumn in the Arctic, the atmosphere is getting cooler, isn't it? But the ocean cools more slowly than the atmosphere. So the ocean tends to be warmer than the atmosphere in the autumn. So what happens if you remove the sea ice cover? Sea ice is a very good insulator. So if you remove that sea ice cover, you're actually heating up the Arctic atmosphere by all that extra heat being released from the ocean, from the newly available area of ocean now that the sea ice cover is retreated. So that is one of the factors that is amplifying the warming in the Arctic region. Another one is the fact that as you're reducing the amount of ice or sea ice and land ice and snow cover in the Arctic, you're actually making the Arctic on average darker by removing all that extra ice and snow. And what that does is to absorb more solar energy, which again, that accelerates or amplifies the global warming in the Arctic region. So that's the second factor that causes the Arctic to warm more rapidly on average than areas of the world that are further south. Next slide, please. And in fact, also with this extra heat that's been released from the ocean into the atmosphere, you get more turbulence and storm systems being generated in the atmosphere. So this is showing one such cyclone or storm system that formed in the Pacific Arctic region a few years ago, and we have satellites that are actually tracking the formation of these. So these do respond, as you're removing the sea ice cover, you get more of these sort of storm systems developing over those sort of newly open areas of ocean. So you're fundamentally changing the atmospheric circulation in the Arctic regions. Now the question is how that translates to weather patterns further south. Next slide, please. This is just showing the extra heat being released. It's a bit technical, this slide, so I won't dwell on it too long, but essentially this is between 60 north latitude and the North Pole, and these yellows, oranges and reds are showing the amount of extra heat that has been released over the last 6 years or so, between 2005 and 2011 in autumn, compared with an previously average conditions. Because basically you're removing more sea ice, which is releasing this heat from the ocean and into the atmosphere. So you're changing the heat structure or thermal structure in the atmosphere, which in turn can affect these storms being generated in the whole atmospheric circulation in the Arctic regions. Next slide, please. And this is really a kind of, this is showing it's not just the sea ice that's been reduced in the Arctic, it's also snow covers. This is a map for last June 2012, when we had, well, this is really illustrating a trend that's been going on for some years, a bit like the sea ice. But the browns on this map has shown where the snow cover is 20–30% below normal for the last 30 years or so, over large parts of northern Canada, at the bottom of the slide, Iceland and parts of northern Russia and Siberia region in the top of the slide. Most areas had snow cover that was below normal last summer, and in fact there's a strong trend of receding snow cover in spring. It's very strong for April, May and June in the Northern Hemisphere. And again, what that does is because you've got less snow cover recently over large parts of the land surface, that means that the land on average becomes darker, it's absorbing more energy from the sun, and that's actually accelerating the warming in those Arctic regions, just like the same mechanism that I mentioned if you remove the sea ice from the oceans. The seawater is darker than the sea ice on average, so you're amplifying the global warming in those Arctic regions. So in other words, it's accelerating the whole processes that are going on in the Arctic. They're these kind of amplifications that are accelerating climate change or global warming through these interactions with the ice and snow at the surface. Next slide, please. And in fact, this is a map which is, I'm beginning to attempt to link now some of these factors. So we have loss of sea ice in the central Arctic. We have snow cover, which is melting. There's more loss of snow cover across the sort of high latitude northern land areas in Canada and in Russia. And also, I haven't mentioned yet, but we have loss of glacial ice in Greenland as well. And at the same time, in the last 6 summers, we've had poor weather over the UK. Why is this? I'll attempt to explain why in a few slides. Next slide. Essentially, the only thing I want you to look at on this slide is this map. This is a map of Greenland. I do a lot of work on Greenland, climate change in Greenland. And this triangle, well, it's not quite a triangle, but this sort of area at the top, this is really an area that I've been focusing my attention on in terms of changes in weather systems over the last, say, 50 years or so. And what we notice, if you go on to the next slide, please, is actually, if you average if you take what we call the, I have this way of defining the pressure systems in that area that you've seen in the previous slide. So how high or low the pressure is over the Greenland and the surrounding sea areas is shown by this green line on this graph here. And don't worry too much about the scale, but essentially, as you go further up the graph, you get higher pressure over Greenland and the surrounding sea areas immediately next to Greenland. And what we've been observing this very high pressure, air pressure over Greenland in the last 6 years, at the same time that we've been getting cooler, wetter summer weather over the UK. And the red line on the graph, this is showing the North Atlantic Oscillation Index, which I defined earlier, which is giving the measure of the strength of westerly winds across the North Atlantic that affects the weather in the UK. So in other words, how low or high the pressure, the air pressure is over Greenland is very closely related to the variation in pressure systems across the North Atlantic as a whole, because the red and the green lines on this graph follow each other very closely, and therefore you can't disconnect the changes in weather in the pressure systems and resulting weather conditions over Greenland from what's happening over the UK. So they are related observationally. We can clearly see that from looking at this graph. Next slide, please. And in fact, actually last summer, it was in the news a lot in July, we had this record melting of the Greenland ice sheet. So what we had was this yellow over Greenland, and the UK is just at the bottom right of Greenland, but Greenland's in the middle of these plots. The left-hand chart shows the air pressure, how unusually high or low it is across the Northern Hemisphere. Where it's yellow, it's unusually high. Where it's blue, it's unusually low. So the UK, we have low pressure last summer. That's why it was so wet and cool last summer. Record wet summer, wasn't it? So you've got blue over the UK, whereas over Greenland you've got yellow. Record high pressure over Greenland, as I showed you on the previous graph, on the right-hand side of that graph, with the green line showing record high pressure over Greenland. But this is showing on the map really sort of related. We've got opposite pressure trends over the UK and Greenland. And in fact, the temperatures, these are showing how unusually hot or cold it was in different parts of the Northern Hemisphere. We've got reds over Greenland, so it's unusually warm over Greenland last summer. At the same time, it's rather cool. We've got light blues over the UK, rather cool summer last summer. So it's cool and wet over the UK, high pressure and very warm over Greenland. Next slide, please. And in fact, actually, last summer is the right-handmost point on each of these coloured lines is a weather station around southern Greenland, as indicated by a black dot on that map here. And actually, these are summer temperatures for these weather stations around Greenland for the last 140 years or so, although they don't all go back for the complete record, but there's a fairly good coverage These are run by the Danish Weather Service. And you can see there's been a very strong warming in Greenland over the last 10 or 15 years. The plot's from 1873 on the left to 2013 on the right. Remember, it's a plot for the summer temperatures, for June, July, August temperatures. And you can see actually the warmest summer of all was last summer at all of these stations, or most of these stations. Next slide, please. And in fact, NASA satellites observed a record melting of the Greenland ice sheets for the first time last summer, for the first time in the satellite record, which goes back to the late 1970s. When for a few days around July 11th, 2012, last summer, you can see the red area here is showing almost complete surface melting of the Greenland ice sheet, something like 97–98% melt. Had never been observed before, such a large area of the surface of Greenland melting in the last 35 years of records. In fact, we've just published a paper extending that record back 50 years. There's been nothing like this for the last 50 years at least, probably over 100 years in fact. A normal summer, you do get melting like on the left-hand graph, so part of the ice sheet surface melts in a normal summer, but it was unprecedented to get a near complete surface melting of the ice sheet. That happened for the first time that we've ever known last summer. So this is actually a result of it being unusually warm over Greenland last summer, which is linked in with the jet stream changes. Next slide, please. And in fact, this is actually, this is the area of Greenland ice sheet that melted last summer. And in fact, each dot is a year for the last 50 years or so. So on average, something like between 30 and 50% of the Greenland surface melts, or melted in the last 50 years. But last summer, for a few days, we had over 90% of the ice sheet surface melting for the first time ever. Next slide, please. And in fact, it's not just surface melting, but you've got an enormous loss of mass from the ice sheet. So hundreds of billions of tons per year, something like 250 billion tons per year of ice has been lost from the Greenland ice sheet each year, averaged over the last 5 to 10 years. And that loss of mass from the Greenland ice sheet, we had a record mass loss last year, almost certainly, that was linked with these warmer conditions over Greenland. And that's contributing to global sea level rise, as all that extra meltwater runs off into the ocean and icebergs break off from the edge of Greenland. Next slide, please. And in fact, this is actually during, because I go on field work to Greenland sometimes, and this is actually a photo. We sail past a gigantic iceberg. Just thought I'd show you a pretty picture of an iceberg in southeast Greenland almost a year ago. Last August I took that. About sort of just over 100 feet long, about 50 feet. No, it's a bit longer than that. 150 feet long and maybe 50 feet high or so. Next slide, please. Sorry, you might need to click that a couple of times. It's a kind of an animation that I stole from another presentation. So if you just click on it a couple of times, please. A couple more. One more time. One more. Okay, so this is an animation of what we think has happened with the jet stream over the last 6 summers. So normally the jet stream, because of the Earth's rotation in part, it's a sort of a ribbon of high velocity air that it comes across the Earth's atmosphere from west to east. But there's always some meanders or waves in the jet stream, because sometimes it meets some obstacle, like Rocky Mountains over North America. So it's sort of diverted or deflected north of the Rockies on the western side, and on the eastern side comes back south again. And so there are always some waves in the jet stream. But in the last 6 summers, these waves or meanders in the jet stream have become more pronounced. So what that means is that in certain areas like Greenland, you've had more air from further south than normal has gone further north over Greenland, which is causing warmer weather conditions there, with a higher pressure over Greenland, which is melting more ice and causing more loss of mass from the ice sheet. Whereas over the UK, we've been on a southward moving branch of the jet stream that's brought generally cooler, wetter conditions, as averaged over the last 6 summers. Next slide, please. Keep going. Okay, so this is actually showing the kind of average jet stream plot. This is showing the sort of winds high up in the atmosphere. Basically, as averaged over the last 6 summers. Can you see there's quite a few meanders? The UK is at the bottom here. Greenland's just at the top left of the UK. And if you follow the dark blue, this is showing the jet stream position, more or less, or sorry, the light blue actually. There's quite a few waves and meanders in the jet stream. During an average conditions for the previous few decades, it's much more uniform, flowing around the world. This is average conditions for 1981 to 2010, in the middle there. But this is for the last 6 summers, in June 2007 to 2012, can you see there's many more meanders in the jet stream, but notably there's a branch of the jet stream that on average for the last 6 summers, one branch of the jet stream has gone further north over Greenland, so it's dragging more southerly air from further south than normal, further up over Greenland, which is causing warm air masses to move further north over Greenland, which is why we had record melt events in Greenland last summer, for example. At the same time, in the UK, which is further east, we're under a different branch of the jet stream, where the jet stream track has tended to come from northwest to southeast, so it's bringing cooler than normal summer weather conditions, but also quite moist because it's still from a westerly direction than normal over the UK. What's also sometimes happened in summer in the last few years is we've had a bifurcation of the jet stream with a branch further south than normal, as well as this further north branch, and that's also affected the UK summer weather. Next slide, please. And in fact, this is showing the what we call the anomalies, or how much the jet stream conditions have deviated from normal high up in the atmosphere. This is for last summer. So the mauve is showing sort of low pressure over the UK, the red is showing high pressure over Greenland. So it's not surprising that we've had that contrast in the weather conditions over those two different parts of the almost two opposite sides of the Atlantic Ocean. Next slide, please. And in fact, as I said, summer 2012 was the wettest in 100 years. Next slide, please. Suggesting that we should all go on our summer holidays to Greenland because you get more reliable summer weather there, although clearly you wouldn't be particularly being sort of carbon friendly and taking all these extra flights to Greenland. But on the other hand, I've gone and done field work in Greenland, so unfortunately I do take flights to go to meetings and things, although I try to minimise, still take more flights than many people, which is not very good really, but it's necessary to go to Greenland to do field work there if you're going to do research. But anyway, next slide, please. There's a theory which comes from a leading climate scientist who I work with. He's based in Seattle in the US, called James Overland. And basically, he has this sort of theory which is linked with the changes in the sea ice. There's also another scientist called Jennifer Francis at Rutgers University in the US as well, who we work with. And a lot of the original ideas came from her, actually. Essentially, they're very, they favour this theory that as you're removing the sea ice and snow cover in the Arctic, this effectively this adds additional heat to the atmosphere from the ocean, as we've seen a few slides ago. And basically, as you're adding more heat to the Arctic atmosphere, you're actually reducing the temperature gradient with latitude. What you normally get is hotter near the equator, isn't it, and colder near the polar regions on average. Because I showed you a slide a few slides ago. Well, we're all familiar with this. You know, if you go to the tropics, it's generally hotter. If you go to the poles, it's generally cooler. And there's constant attempts to sort of to try and sort of equalise any temperature gradients. But the thing is, the issue is, if you're removing more sea ice from the Arctic, you're warming up the Arctic faster than you're warming the regions further south. So you're actually reducing that heat gradient across a range of latitudes. And the basic idea is that by reducing the heat gradient across a range of latitudes, because you're warming the Arctic more strongly than further south, you're potentially reducing the amount of energy available for driving the jet stream in summer. So it meanders and slows down as a result. It becomes more locked in position with respect to various places on the Earth's surface in the middle latitudes. So it's possible, it's not been proven yet, but we're working on the idea that this can be a key mechanism that may cause the jet stream to become more locked in position in summer, where the waves in the jet stream become more pronounced. The jet stream also slows down. So in effect, you can get more extreme weather various places in the middle latitudes of the Earth's surface, like the UK, for longer periods of time. You can get more extreme weather. And this may be why we've had these sort of record wet summers in the last 6 years, as well as the record warmth and loss of ice in Greenland. But basically, the computer models that are used to simulate or predict climate change do not understand, they don't really sort of properly capture these changes in the jet stream, because these are very recent observations that we've made of these changes. So in other words, there's some great uncertainty in how we actually can predict changes in regional climate. because the computer model simulations are not really up to the job, because we've been observing these interesting things that no computer model was predicting, say, 10 years ago. And also there is year-to-year variability, so even though you might have various factors that cause the jet stream to vary position, in certain years some factors might be stronger than other factors, so you wouldn't necessarily expect every year to be, say, have a wet, cold summer in the UK because of this effect, if it's proven to occur. So you can still get hot, dry summers in the UK. It may be that perhaps that they're just less frequent than before. Next slide, please. And in fact, actually, this is an example of where the computer model predictions, these are used to simulate what's going to happen with the sea ice in the Arctic for the next 100 years. So each coloured line is a computer model prediction of what's likely to happen with the Arctic sea ice cover between, say, we're here now, we're in the middle of this slide, and 2100, say 85 years in the future or so. And the idea is the amount of sea ice in the Arctic is predicted to decline, as you might predict as the world gets warmer, but there's a lot of uncertainty, isn't there, between all those predictions. So scientists tend to take an average prediction from all these models, because there's a huge range of uncertainty with what we understand is going to happen with the climate, and there's uncertainty in the computer models themselves. But the line to look up on this graph is the black line. This is what the Arctic sea ice area has actually been doing in the last few decades. So we're now at the end of this black line. The end of the black line is last summer, 2012, when we had that record loss in the Arctic sea ice cover. This is the sea ice cover that has been observed to change in the Arctic from satellite data. So these are real data. What you notice is that the real changes in the Arctic sea ice cover, as shown by the black line in the last decade or so, have been a lot more rapid than predicted by most computer model simulations of what the sea ice is expected to do. So in other words, if anything, the computer models that are used to predict changes in the Arctic climate and sea ice are actually rather conservative and slow compared with what's actually been observed to occur over the last decade. So we've had some interesting surprises just looking at what's happening with the climate and the sea ice in the Arctic, where the changes are actually more rapid than the climate scientists were predicting they would be. So that's actually rather worrying in a sense. Some part of that may be natural random variability, but I doubt all of it. There is, I think, a real signal from human greenhouse gas forcing in there, in that we're actually affecting the climate quite dramatically in the Arctic regions, certainly over the last 10, 15 years. Next slide, please. I'll skip this one because I'm almost out of time. Yes, well, in fact, we're almost at the end slide anyway. But just to briefly say that sea ice changes and snow cover changes are not the only factor that can cause the jet stream to shift position and strength. You have other factors like variations in ocean temperatures that I mentioned. So to be fair, I just wanted to briefly mention these because I know, people at the University of Reading, the Met Office, are doing a lot of work into this, so I think it's only fair to mention. So the next slide, in fact, if you just, this is actually some bit of work. I mean, I work occasionally with sea temperature records, and it's really interesting. I work at the Iceland Met Office, and the green line here, this is actually showing what I sort of laughingly abbreviated to NICE SST, North Icelandic Sea Surface Temperature Record, which is a kind of a good approximation of the sea temperatures at the surface across that part of the North Atlantic, just north of Iceland, which is where you get the warm Atlantic water currents tend to meet the cold polar ocean currents that are moving down from further north. And what you can see is there's been can you see that there's a strong warming of the water masses north of Iceland over the last, over the last 140 years, since the 1870s. It's been I just updated it a few weeks ago, so you've got very up-to-date data to early this year here. But it's not a uniform warming. There have been parts of the 20th century between the 1930s and the 1970s where on average it was actually the sea temperatures were getting colder. Other times between, say, 1900s and the 1930s where you had a really very rapid warming, and again recently. And there's a sort of a long-term cycle, about sort of 50, 60-year cycle of warming and cooling superimposed on a long-term warming trend. So it's not just a linear increase, but there's some cycle in the data as well. And at the moment we're on an upward cycle in the North Atlantic sea temperatures, apart from global warming, or in addition to global warming, which is why we've had such an enhanced warming in the green line on this graph. And Met Office scientists, some other scientists, suggest that this could be a major factor that is causing the jet stream to vary position and strength in summer. And particularly if you get a branching jet stream that comes further south than normal over the North Atlantic, because the sea temperatures are higher over the North Atlantic than they have been a few decades ago, this means that that jet stream, if it's further south, is picking up more energy from that warmer seawater, and it's actually can invigorate the jet stream and give you more storm systems, low pressure systems and rainfall over the UK. So there's also complex patterns of these sea temperatures as well. I won't go into it in detail, but it's another factor that can cause the jet streams to change position and strength and affect our summer weather over the UK. And we know that these real changes in the sea temperatures over the North Atlantic have been quite pronounced recently. So I need to mention that as well. Next slide, please. In fact, that's my last slide. So in summary, global warming is driven through human activity. It's not a uniform process, is it? It varies regionally across the world, but also with time as well. So if you look back at various weather and climate records for the last century, you can see that there are ups and downs in the temperature. It's not just a straightforward increase. Well, this is the problem when you look at the computer model projections for the next century. They show these nice curves going upwards, but in reality we know there's a lot of ups and downs. Well, you see this just from looking at the day-to-day weather, but also in the longer-term climates as well. And I don't think the computer models adequately capture those ups and downs yet, because the computer models do not really simulate very well the changes in the jet stream positions and strength. So human-driven global warming, it's not a uniform process. It can spring surprises, as we've seen in the observed record of what's actually happening with changes in the Arctic in the last decade or so, but also changes in the UK summer weather conditions, where suddenly we've had this run of wetter, cooler summers, and of course the computer model predictions, we're saying we should have hotter, drier summers in the UK, and they weren't really predicting this from the computer models because they tend to predict a smooth linear sort of curved increase, a smooth curved increase in the temperatures. But of course there's a lot of potential short-term variations, but also there are other factors that the models don't include. So the tendency over the last 6 summers, certainly the UK has tended to have wetter, colder summers, but at the same time, and it's almost certainly related, Greenland has had warmer, sunnier summers in the last 6 years, and that in itself causes a problem because you've had all this extra ice being lost from Greenland, which runs off into the ocean and is accelerating the rate of sea level rise globally, which can affect coastal communities potentially going into the future. What we've also noticed is that the jet stream has slowed down. It's become wavier over the North Atlantic in the last 6 summers, and you get more year-to-year persistence, so more locked-in weather conditions at various points on the Earth's surface, including the UK and Greenland. So we've had more year-to-year persistence in recent unusual large-scale weather patterns, whether that be cool, wet summer weather conditions in the UK or unusually dry, warm, sunny conditions over Greenland. I actually got badly sunburned doing field work in Greenland a couple of years ago because it was so sunny when I was doing the field work there. But they've had a lot of unusually sunny weather over Greenland the last 6 summers. Essentially, we think that these changes in the jet stream that I've been discussing may be influenced by earlier seasonal losses in Arctic sea ice cover, where we've lost something like half of the Arctic sea ice in late summer over the last 30 years or so, and also the reduction in snow cover, which is amplifying or accelerating global warming in the Arctic regions. What we've also noticed from my own research is there's more high pressure systems over Greenland, also over the eastern parts of the US and Canada, which is actually linked in with this sort of wavier jet stream, where you're having this sort of blocking high pressure, as we call them, developing more strongly on the North American side of the Arctic in the last summers. These can actually deflect the jet stream winds in turn once these weather systems form. So you have more persistent and wavier jet stream patterns with locked-in weather conditions at the surface. And because the UK is downwind or downstream of Greenland is like a big stone in a river current. So you end up with a jet stream that gets diverted more readily up over Greenland. So we end up with the sort of well, we're on the lee side of Greenland, aren't we? Just like if you're downstream of a stone in the river, then you get the water that gets deflected either way around the stone. So we tended to get these jet stream conditions in summer, where it's either come from further northwest than normal, having been deflected all the way north up round Greenland, or further south than normal. Sometimes you actually get a bifurcation of the jet stream around Greenland, so you can get this jet stream winds from either further south or further northwest, but either way, it tends to give us wetter, and if it's from the northwest, cooler summer weather conditions. linked in partly with these sort of higher sea temperatures in the North Atlantic, relating to this more southward branch of the jet stream. But either way, there have been some very interesting changes in weather patterns over the last 6 summers, but goodness knows how it's likely to continue. It's very dangerous to make predictions based on 6 years of data, of course, and we just have to wait and see what happens to see if these trends continue. So I don't pretend to have all the answers, but I'll be happy to try and answer any questions. Thank you very much.